the military's high-tech vanishing act, a masterful blend of contours and composites that makes aircraft invisible to radar. This sky-high sleight of hand is now coming down to earth and setting out on the high seas. Daunting, deadly, top secret. Now, stealth technology on Modern Marvels. Sleek, lethal, powerful. The F/A-22 Raptor opens a new era in stealth technology. The revolutionary concept that's changed the face of aerial warfare since the 1990s.
Compared to anything else that's out there, this airplane is head and shoulders above those jets. We can get to places very quickly before people would expect us, and with stealth there, they don't know that we're going to be there.
The Raptor, like all stealth aircraft, reduces its observability in 5 distinct areas. Visual, acoustic, heat, infrared, and most of all, radar. Radar, short for radio detecting and ranging, locates an object by transmitting ultra-high frequency radio waves. By measuring the time taken for the radio waves to be reflected back to the transmitter, the location, speed, and size of the object can be determined. One of the best ways to reduce the chance of detection is to create aircraft with the smallest possible radar cross-section, or RCS. An aircraft's RCS can be reduced in 2 fundamental ways. First, specially designed contours built into the airframe help deflect radar away from the source. The earliest stealth aircraft accomplished this using flat panels. The latest generation of stealth has curved panels. The second way for a plane to minimize its radar cross-section is through the materials that coat the airframe. Those materials help absorb or trap radar signals rather than reflect them. The composition of these radar-absorbing materials, or RAM, remains classified. With the F/A-22 Raptor, stealth technology has come of age. Manufactured by Lockheed Martin in partnership with Boeing and Pratt & Whitney, it measures more than 62 feet long, with a wingspan of more than 44 feet. Yet its radar signature is smaller than a sparrow's. In the past, achieving such invisibility required compromising aerodynamic performance. Case in point, the Raptor's revolutionary predecessor, the F-117A. But the F/A-22 is as speedy and nimble as it is stealthy.
If you compare the F/A-22 to a 117, you'll notice that ours is very smooth, curved shapes, and basically where that helps us is in the aerodynamic capabilities of the airplane. We are much more agile, much more capable than the F-117, which is basically a series of flat plates, which greatly affects their aerodynamic agility capability.
Designing a stealth aircraft is really not rocket science. First thing we do is we take care of shaping. Once you take care of the shaping portion of it, you've done about 90% of the stealth. And in the area of shaping, what we worry about is what we call planform shaping.
Planform shaping is an airframe design strategy in which leading edges are aligned along identical angles. The goal is to predict and control the direction that radar waves bounce off surfaces, a phenomenon called scattering. The Raptor sports another key element of effective shaping. Unlike conventional planes, which feature protruding navigation and communications gear, the Raptor integrates such equipment seamlessly within its airframe.
As you look at the airplane, you notice that it's basically smooth. There are no antennas or anything sticking out of the airplane that you would see on other aircraft. And that's because we've taken all the antennas and sensors on the airplane, and they're embedded in the leading edges, trailing edges in the aircraft itself. You can see right here, this large panel is actually our UHF radio antenna. There's one on the bottom here, there's one on top of the wing. If you were to look at an F-15 or F-16, you'd see a blade antenna, and that's what they're using, where ours are smooth like this.
Using the Raptor's advanced stealth technology, a pilot can soar undetected in enemy airspace long enough to deliver his deadly arsenal and return home unscathed.
The reason we carry all the weapons internal is for stealth reasons. With everything internal to the airplane, you don't have an increased radar cross-section, so people can't see you as well. And when it comes time to employ the weapon, the doors open quickly, the missile is released, and then the doors close back up to put us back in that stealthy configuration, so people can't see us.
Since straight lines or seams on a plane easily reflect radar, every door on the Raptor features saw-toothed edging, from weapons bays and landing gear to maintenance access panels. The Raptor's cockpit canopy is another triumph of stealth design. Radar can penetrate a conventional canopy and reflect off the cockpit interior and the pilot himself. To counter this effect, previous stealth generations were forced to compromise the pilot's view. But the Raptor's radically redesigned 11-foot-long canopy grants the pilot a 360-degree view.
To make sure that we don't get scattering from the cockpit or from the pilot's helmet, we put specialized coatings on the canopy that provide it the conductivity so it looks just like a metal plate, and energy reflects off of that rather than going into the canopy and reflecting back out.
The Raptor's stealth technology is coupled with an advanced propulsion system called Super Cruise. New Pratt & Whitney engines with increased thrust-to-weight ratios enable the Raptor to cruise for extended periods at supersonic speeds without the added thrust of afterburners. Earlier jet fighters, known as legacy aircraft, use afterburners when they need an extra boost for carrier liftoffs or for supersonic speed.
Typically, when we go into an afterburner mode on a jet engine, that's accomplished by effectively just squirting jet fuel into the exhaust system and lighting it off. And we don't need to do that to be able to go super cruise.
Super Cruise enables the Raptor to go faster, farther, and longer than any previous jet. The longest a legacy aircraft can continuously fire its afterburners is about 15 minutes. The Raptor can operate in Super Cruise mode for almost a half hour.
A lot more sustainment, a lot more speed on the battlefield over a longer period of time.
Between stealth and Super Cruise, we have the ability of surprise, or the capability of surprise. People don't know we're there, and we can get there very quickly, and they just don't have the time to react to what we're doing.
Pilots can get a taste of the FA-22's combat prowess here at the Raptor's nest. This cockpit demonstrator shows the advantages of stealth technology in combat.
We're going to fly a practice mission here to give you an idea of what the FA-22 is capable of doing. We're at 40,000 feet right now.
The Raptor's exact radar signature is classified, so the display features a notional or approximate range.
We've got the own ship, the FA-22, right here in the middle of this defensive display with this blue notional signature ring around it. That indicates that the airplane is a stealthy airplane.
Just a flip of a switch shows the difference stealth makes. With the Raptor's stealth disabled, its radar signature more than doubles in size. But in stealth mode, the Raptor can infiltrate enemy territory, destroy targets, and withdraw before it's detected. Even if confronted by an enemy fighter, the pilot can trust in the Raptor's agility and weapons to get the first look, the first shot, and the first kill.
And we can rule the day as an air dominance fighter in this century. This is a fighter pilot's dream.
The dream of inventing the ultimate countermeasure to radar dates back to World War II and the Battle of Britain. In 1940, the Nazi juggernaut was poised to control all of Europe. Only England and the Royal Air Force stood in Hitler's way. But the RAF was just 1/10 the size of the German Air Force, the mighty Luftwaffe. For nearly 3 months, the RAF and the Luftwaffe waged daily battles above Great Britain for control of the skies. Although Germany had a tremendous numerical advantage in planes and pilots, British tactics and technology were superior. Hermann Goering, the head of the Luftwaffe, thought it was uncanny that the RAF always seemed to be in the ideal position to intercept German air attacks. It wasn't uncanny. It was radar. The RAF had the huge advantage of knowing where and when the Luftwaffe would attack. They could even determine the size, speed, and heading of the attack force and be ready to pounce on it from above. Without control of the skies, Adolf Hitler was forced to abort the invasion of England. Since the end of World War II, radar has made it nearly impossible for warplanes to attack an enemy without being detected well in advance. In the late 50s, the U.S. learned of great advances in Soviet radar and missile technology. The wake-up call occurred in an era when U-2 spy planes were flying over the Soviet Union.
The U-2 was one of the great advances in aircraft technology. It was an incredible leap in an ability to fly over an enemy's territory, fly above his ability to see you on radar, fly above his ability to employ fighters against you at a key moment in the Cold War.
But on May 1st, 1960, U-2 pilot Francis Gary Powers was shot down by a Soviet surface-to-air missile. It marked the first time in history that a missile had brought down a plane. Powers survived the crash and was convicted of espionage in Moscow. U-2 flights over Russia were halted.
Two things I think really precipitated us to really go after stealth as a matter of national priority, and that was the downing of the U-2s and the realization that the penetrating bombers that we had could no longer penetrate the critical Soviet Union airspace.
Soviet advances in radar and surface-to-air missile technology now made it harder for the U.S. Air Force's Strategic Air Command, or SAC, to accomplish one of its primary missions: penetrating Soviet airspace and reaching key military targets deep within the Soviet Union. Leaders in the Pentagon reasoned that if the Soviet Union no longer feared the U.S. Air Force's ability to retaliate after an attack, it might be tempted to launch a nuclear first strike. It became a top U.S. priority to develop tactics or planes that would circumvent Soviet radar defenses and shift the balance of power.
In the 1970s, you had the Air Force saying, we want a capability to be able to go into a hostile area without radar seeing us.
In cooperation with the Defense Advanced Research Projects Agency, or DARPA, a scientific bureau within the Defense Department, the Air Force initiated a special research program. It asked the leading military aircraft manufacturers to present proposals for a warplane with the smallest possible radar signature. Ironically, one of the companies not asked to enter the competition was the most respected secret think tank in the aerospace industry, Lockheed's Skunk Works. Skunk Works was named after a foul-smelling secret moonshine still featured in Al Capp's Lil Abner comic strip. It had earned a reputation as the preeminent creator of exotic high-performance aircraft, including jets like the high-flying U-2.
We were not asked to participate. Basically, they went to the fighter houses of the day. People had fighters in production. We didn't. We were not currently building a fighter. So we were not in the ballgame, so to speak.
But Skunk Works had a secret. It had already ventured into low observable technology for their #1 client, the Central Intelligence Agency. Amazingly, throughout the 1950s, the CIA had its own air force of sophisticated spy planes. Their greatest spy plane was the SR-71 Blackbird. It was capable of speeds in excess of 2,000 miles per hour at altitudes over 80,000 feet. It was specially shaped to defeat radar. Its wings, tail, and fuselage were loaded with special composite materials and iron ferrites that absorbed radar energy. In addition, the leading edges of its wings were lined with a radar-absorbing structure, or RAS, that trapped radar energy. Skunk Works' problem was that all the Blackbird's design features were classified and property of the CIA. But Ben Rich, the head of Skunk Works, persisted and eventually won the CIA's permission to reveal the secret data. Lockheed was permitted to enter the stealth or low observable competition. Now all Skunk Works had to do to win was build an invisible airplane. Fortunately, they had someone who thought he could do it. Lockheed Martin assembles the F-A-22 Raptor in Marietta, Georgia. with parts manufactured by more than 1,000 suppliers in 42 states. Stealth technology will return on Modern Marvels. The march of stealth technology began with one revolutionary aircraft, born of a secrecy as black as its titanium airframe. What the Wright Flyer was to aviation in its earliest days, the F-117 Nighthawk has been to stealth technology.
From a historical standpoint, people are going to look back on the F-117, and it will certainly be a milestone. And it's just amazing to me that the thing was designed over 30 years ago, and it is still, bar none, the best out there at what it does. And you need somebody to go in and provide precision munitions. There's nobody else to call, in my opinion, other than the F-117.
Developed by Lockheed's Skunk Works, the F-117 was the first stealth aircraft to be tested in combat. On December 19, 1989, 8 Nighthawks took part in Operation Just Cause, the military invasion of Panama. But it was Operation Desert Storm in 1991 that brought these fighters public acclaim. In nearly 1,300 missions, they accounted for 40% of all targets eliminated in the war. Despite the presence of hundreds of anti-aircraft artillery batteries and surface-to-air missiles, not a single stealth fighter was lost, proving the old axiom, you can't hit what you can't see. Lieutenant Colonel Joseph Salata was based with a 37th Tactical Fighter Wing Night Stalker Squadron in Saudi Arabia. He flew the F-117 in the first wave of black jets to attack Baghdad.
We sort of believed in stealth technology, but we hadn't really proven it at the time. I mean, we had done it in radar tests and so forth, but never in actual combat when there were actual bullets flying at you. So there was probably just a little bit of nervousness there until we saw what happened on the first night, and we saw how successful we really could be, and we saw that the Skunk Works really did design a great stealth airplane.
The F-117s destroyed Saddam Hussein's key command and control centers, the heart of his integrated air defense system, and vital communication centers. In just one night, the black jets all but eliminated Iraq's ability to wage a coordinated war.
We had mission success rates that were unprecedented. You could almost guarantee that a target was going to be taken out by a stealth as long as we didn't have problems with weather or maintenance on our aircraft or something like that. As long as we got to the target, we had a very high success rate of killing that target.
The mysterious black jet sent shockwaves around the globe, putting military planners and governments on notice that every defensive radar system in the world was now useless against stealth technology.
This really changes the nature of warfare. To be able to go into a foreign country, be able to destroy a target without them even knowing you're there until the target's destroyed. They didn't know we destroyed those targets. They didn't know these planes were in country until there was smoke over Baghdad.
12 years later, in Operation Iraqi Freedom, the F-117 once again ruled the skies.
As far as what was it like to fly the stealth in Operation Iraqi Freedom, well, I'll be honest, I was a little bit nervous the first night. And so you rely on your training, and everything just kind of starts to flow, just like a normal type of sortie.
Throughout that whole campaign of over 100 sorties and 500 or 600 hours of flying, aircraft never took a scratch, and we were able to have about a 92% hit rate. Every combat mission that I flew in OIF, I never felt like I was being tracked. And I think from that standpoint, LO, paid for itself right there. You can get in there and get out and get your job done.
The combat success of the F-117 has set the standard for all low observable technology. The plane's origins date back to the early 70s, when the Pentagon asked military aircraft makers to submit designs for a fighter jet with reduced radar detectability. Those with the best design would win a contract to build 2 demonstration planes, codenamed Have Blue. In 1975, Dennis Overholzer was a 36-year-old software designer specializing in electromagnetic problems. In early May, Skunk Works project manager Dick Shearer asked him to solve an interesting problem.
Dick Shearer then asked me, how should we shape an airplane to make it invisible? And I says, well, it's rather straightforward from a radar cross-section viewpoint. I says, you just make it out of a lot of flat panels. You tilt the flat panels over, and you sweep the edges on the panels, and you put this together with a bunch of these flat panels. Well, Dick said, you've got to be kidding me, he said. Nobody says that. I said, well, you asked.
Overholser created new computer software called Echo 1. It calculated how each surface of a plane would scatter radar or electromagnetic waves that struck its surface. About a year later, the march towards stealth was advanced by Overholser's mentor, a retired former skunkworks mathematician named Bill Schroeder. He came across an obscure scientific work written 15 years earlier by a little-known Russian physicist named Peter Ufimtsev. Ufimtsev had shown how to predict the directions a geometric configuration would scatter electromagnetic radiation. For skunkworks, it was like finding the Rosetta Stone of stealth technology. It now had the design principles that would lead to the F-117.
The aircraft was designed 30 years ago by Lockheed Martin in the late 70s. And what they utilized was a type of stealth technology called a faceted shape design. And what that does is confuses any kind of radar signal, and consequently we're able to maintain, for the most part, invisible against anybody that may be trying to detect our presence out there.
The discovery of Ufimtsev's work accelerated skunkworks' plans for a flat-panel stealth design. It looked promising in theory. The only question now was how to make it fly. During World War II, the Lockheed plant in Burbank, California, was given a stealth treatment of its own. As a precaution against enemy air raids, the plant was hidden beneath sheets of fabric painted to look like a suburban neighborhood. Stealth technology will return on Modern Marvels. To this day, experimental stealth aircraft are born under a cloak of secrecy. In October 2002, Boeing unveiled its Bird of Prey. The once highly classified project ran from 1992 to 1999, testing technologies that are now industry standards. Two more recently revealed top-secret programs are a stealth helicopter, the RAH-66 Comanche, and an unmanned surveillance vehicle called the Dark Star. But no aircraft's evolution was ever as closely guarded as the F-117's. In the race for stealth technology in the mid-70s, Lockheed Martin put its money on an ambitious design. Skunkworks designers created a sketch for a plane made completely of flat sides. From above, the plane resembled an arrowhead or a diamond that had been beveled in 4 primary directions.
My good friend Dick Cantrell was head of aerodynamics, and of course, as one might expect, when Dick first saw some of the stealth designs we were coming up with, specifically our first diamond-shaped object, which he named the Hopeless Diamond, he had some serious doubts about it, and he came to me in kind of a confidence off to the side one day, and he said to me, he said, Dennis, is this really as low a cross-section as you're claiming? And I said, yes, it is. Dick thought for a moment, and then he says, well, he says, in that case, he says, we'll teach it to fly.
In 1976, Lockheed took a 10-foot model of their plane to the Air Force's radar test range. The results of the tests stunned both DARPA and the Air Force and won the development contract. Skunkworks had presented them with an aircraft that had the radar signature of an insect.
The results were dramatic, to say the least. Two things happened immediately. The first of which is this fairly unclassified white world program immediately became black and was classified top secret. And black means in this context not just top secret, but unacknowledged. It was as black as the Manhattan Project. The other thing is DARPA and the Air Force and Lockheed got together and mutually funded the development of 2 low observable technology demonstration aircraft, the Have Blue aircraft.
The challenge now was to build a real airplane loaded with all kinds of non-stealth things, like a cockpit, engines, exhausts, and a pilot. The final Have Blue design was like nothing ever built, perhaps because it was the first ever conceived by electrical rather than aeronautical engineers. The plane was 39.8 feet long and weighed around 12,000 pounds. The leading edges of the wings were swept back to a razor-sharp 70 degrees. In late November 1977, the engineering team flew Have Blue to a secret airstrip in the Nevada desert. It was unloaded at night and placed in a hangar to conceal it from the prying eyes of Soviet satellites. On December 1st, 1977, Have Blue took to the skies for the first time. The fact that the plane even flew was an engineering miracle.
The instability of the aircraft in pitch-yaw roll, of course, pitch being the longitudinal force of the aircraft and roll, and yaw, its side slip. So the parameters that control those motions of the aircraft were very, very critical in the development of the airplane. The original Have Blue airplane was the first aircraft to ever fly that was unstable in all three axes. And without fly-by-wire flight control systems, there would not have been a Have Blue airplane.
Fly-by-wire flight control replaces mechanical controls with wires, sensors, computers, and actuators. In the decades since the flight system helped get Have Blue off the ground, it's become standard equipment on all stealth aircraft.
And these are the pitot tubes that the aircraft uses to tell it where it's at, how high it is, how fast it's going. All four of these are hooked up to their own individual computer systems.
Even though the pilot of a fly-by-wire system still uses the standard stick and pedals, the computers assist by making constant adjustments. On November 16, 1978, the Air Force ordered 5 full-scale prototypes, or YF-117As. Skunk Works now had to adapt their design to account for such non-stealth items as a bomb bay, a weapons targeting system, radio antennas, and still keep it stealthy. The big question was, could it be done? F-117s carry detachable radar reflectors when they are not in stealth mode, so local air traffic controllers can track them. This limits the potential for accidental collisions with these invisible planes. Stealth technology will return on Modern Marvels. Stealth technology's prowess in the skies is matched by astronomical budgets. Current production plans for the F-A-22 Raptor total 279 jets at $133 million each. In response to such high costs, the Defense Department commissioned the construction of the F-35 Joint Strike Fighter, a stealth warplane that can be adapted to meet the needs of each branch of the military. Whether designed for conventional airstrips, aircraft carriers, or even vertical liftoff and landing, the F-35 brings stealth capability to the field for between $28 and $38 million per plane. Such flexibility and affordability were unimaginable when history's first stealth aircraft was in development. The first prototype of the stealth jet, the YF-117A, was completed in the spring of 1981. It weighed 52,000 pounds and was 65 feet long, much larger than Have Blue. The wider shape of the plane met the Air Force's requirement that it carry up to 5,000 pounds of munitions. To accommodate the internal bomb bay, the prototype's swept wings were much broader than the original Have Blue. The F-117 has a similar structure today.
This is commonly referred to as a MAU 12. Anyway, this is where our ordnance hang on, and it's in the down configuration. It's called a trapeze, and it actually will swing up into the airplane, and then they'll close the doors. And that reduces our exposure to the radar that are looking at us. So we come in, the door's open, the bomb comes off, the door's closed very, very quickly.
A desert camouflage scheme disguised the prototype's facets during daytime flight testing. The Air Force requested that all future planes be painted black for their intended role as night fighters.
The F-117 is designed and has operated at night. This goes back to the Black World origins of the F-117 and continues to this day. It is a night fighter. It proved that stealth technology does work. The F-117 is an incredible aircraft that has far exceeded any expectations.
The Air Force ordered 29 planes. Eventually, Lockheed would produce 59 F-117s at a cost of $42.6 million per plane.
One of the hardest challenges was the fact that we wanted this airplane to look just like the Hopeless Diamond. We wanted perfectly flat, angled surfaces to appear to the radar. But to fly it, we had to take in air, we had to exhaust air, we had to have lights on the wingtips, we had to have a canopy for the pilot, we had to have an aperture for the infrared system to see through. So we ended up creating solutions, very innovative solutions to all of those challenges.
Among the most innovative of these was the platypus tail.
What the platypus does is shield the exhaust system of the airplane, which is very flat and very wide. All of the air that comes out of the engine is hot and washes over the platypus exhaust, which is basically constructed of high temperature ceramic brick. And that brick is almost identical to the space shuttle tiles.
Instead of funneling all of the exhausts in a small location, what they did is they spread it out, and they utilized a special composite material on the aft end of the tailpipes, if you will. And what that does is also help to minimize the exhaust temperature. So hiding not just from the radar lookers, but also anybody that may be trying to see us from an infrared standpoint.
To further decrease the prototype's heat signature, engineers eliminated afterburners, which raised engine temperature by about 30%. In October 1979, the Air Force formed the 44 50th Tactical Fighter Wing near Tonopah, a remote town in the Nevada desert. The U.S. Air Force gave Colonel Bob Jackson the task of assembling the elite group that would make the F-117s operational. Lieutenant General Dennis R. Larson was a young captain when he was recruited for the secret program. His first interview with Colonel Jackson was typical of those conducted with the program's other pilots.
When I walked in the door, he said, "I want to hire you for a job. All I can tell you is that it's a great job. I can't tell you where you're going to live, except for it's going to be in the desert. I can't tell you whether you're going to be flying, and that's all I can tell you. Are you interested?" And I waited about 2 seconds, I think, or something like that, and says, "I'll take the job."
At Tonopah, pilots were introduced to the black jets in a scene right out of a Hollywood movie.
Normally we tried to show the pilots the airplane in the dark at night with the hangar doors just partially open, big American flag over the top of the airplane hanging from the top of the hangar, and your heart just kind of got up into your throat.
For security reasons, pilots were forced to sleep during the day and fly at night for the first 6 years.
The people who worked on that fighter when it was still in the Black World referred to this as the vampire convention, because they would have to rush home, get the aircraft in the hangar, and be back by sunrise.
The F-117A came out of the black on November 10, 1988, when the Defense Department released this purposely fuzzy photo to the public. Just 12 days later, the public would get its first look at another top-secret stealth plane, the B-2 bomber. By that time, the B-2 had been in development for 7 years. It started in 1981, when Northrop's Advanced Systems Division won an Air Force competition to design a plane that could fly long distances, carry a large payload, and invade an enemy's air defense system. In short, a stealth bomber. Thanks to a decade of advances in computer technology, it was now possible to project the results of Ufimtsev's computations over curved or rounded surfaces. Instead of flat surfaces like the F-117, the stealth bomber would have a smooth, curved shape. The more aerodynamic shape would allow the B-2 to increase its lift and lessen its drag, enhancing its performance as a long-range aircraft required to carry 40,000 pounds of bombs, 6,000 nautical miles.
The F-117A could employ 2 weapons against a precision target anywhere in the world at any time. The B-2 is the next generation of that. And you've gone from being able to destroy 2 targets to destroying up to 16 targets at one time.
Northrop based its design on a large flying wing, an aerodynamic concept pioneered 30 years earlier by the company's legendary founder, Jack Northrop. In the late 1940s, Northrop had unveiled his innovative giant 4-engine bomber, the B-35, as well as the jet-powered YB-49. But control systems of that era had trouble making the flying wing a stable bombing platform, and Washington lost interest in the concept. Based on the B-2 mission requirements, Northrop engineers determined that the ideal width for the B-2 was 172 feet, the identical width of Jack Northrop's original flying wing. One remarkable innovation on the B-2 was the extensive use of carbon fiber epoxy composites. Lighter than aluminum and stronger than steel, these composites also help absorb radar. The outboard section of the aircraft included a 65-foot section made entirely of composites. In fact, the B-2 is made of more pure carbon fiber material than metal. Both the F-117 and the B-2 reach top speeds of about 650 miles per hour, just shy of Mach 1. Neither carries guns or air-to-air missiles. They depend on stealth for survival, not speed or weapons. Both planes showcase stealth technology's role as a force multiplier.
A force multiplier is the ability to destroy a target, to inflict the intended damage on an enemy with a smaller amount of force. In Operation Desert Storm, you have one airplane, the F-117, able to destroy one target, guaranteed with precision accuracy. When you go on to the next level of technology, you have the B-2. Or now with one airplane, you can destroy 16 targets, which really changes the whole nature of warfare.
We are asked to do a number of different types of missions, one of which is to take down enemy radars, enemy SAM sites, and things like that. What that does is it enables other aircraft that may not be as stealthy, but may carry a lot more ordnance, fly through that breach in the armor, and then get their job done too.
Stealth's mastery of the skies has become legendary, but that's not the only place this cutting-edge technology is making a big splash. In October 2001, B-2 stealth bomber crews set records for the longest sorties ever flown in combat. Refueling in midair, they flew from Missouri's Whiteman Air Force Base to Afghanistan and back, staying aloft for about 44 hours. Stealth technology will return on Modern Marvels. In the mid-1980s, while still top secret itself, the F-117 spawned a surprising descendant, the Sea Shadow, stealth's first sea craft. Operated by Lockheed Martin for Naval Sea Systems Command, it has a radar signature no larger than a dinghy's.
One of the most characteristic things about this ship is its faceted hull. Everything is at an angle, nothing presents a flat, broadside view anywhere.
Because the Sea Shadow operates in the water, it must contend not only with radar, but also with a second detection system, sonar. Short for sound navigation ranging, sonar sends an acoustic pulse through the water. When the sound waves encounter an obstacle, they reflect or echo back to the source. Sonar calculates distances by measuring the time it takes for that echo to return. A faceted surface proved to be as stealthy in the water as in the sky. The Sea Shadow can slip through both radar and sonar. But in open water, such total success is a liability. Ocean waves show up on radar, and the Sea Shadow left an open hole in the water pattern. Sea Shadow's designers at Lockheed Martin solved this problem, but they're not telling how. That's no surprise for a vessel born under a cloak of secrecy. Like the F-117, the Sea Shadow was built under top-secret security. Components were delivered at night and lowered through the retractable roof of this barge. In 1985, the entire barge transported the vessel to a secret test range for sea trials. the same barge is Sea Shadow's home today, moored at the U.S. Naval Station in San Diego.
Sea Shadow is what's commonly referred to as a swath hull design. SWATH stands for Small Waterplane Area Twin Hull Vessel.
The Sea Shadow's hull design is key to its stealth. Standard V-shaped hulls create a ship's most evident signature, its wake. Wakes can be detected not only by radar and sonar operators, but also by aerial surveillance teams, leaving ships vulnerable to attack. Sea Shadow's unusual hull is specially designed to avoid creating this telltale signature.
At the end of each strut is a lower hull section of the length of the ship and about 10 feet in diameter. The only part that actually cuts the surface of the water are the two struts that go to the lower hulls, and they're very long and narrow and pointed on the ends, so they create little to no wake as we go through the water.
The near constant vibration of engines and generators, a dead giveaway to sonar detection, presents another challenge to stealth technology at sea.
We have vibration eliminators in all piping systems. Most have two angles to them. You have a vertical vibration eliminator and a horizontal eliminator. We'll go around the corner and we will see another type of system that eliminates the vibration from the equipment itself. This very large engine is mounted on 4 vibration eliminators. Those are in the foundation of the unit, and they prevent the vibration and the noise from this large diesel engine from transmitting to the hull and thus into the water. Those 4 mounts are located at each corner. You can see that they're a thick substance. They're an elastomeric rubber. The bolts go through those to prevent the machinery from tilting, but yet the machinery is totally isolated from the steel hull of the ship through that cushion.
Inside and out, every element of the Sea Shadow contributes to maximum stealth. Topside hatches have saw-toothed edges and retractable cleats for mooring lines.
If we're in a situation where we might want to clean the deck and reduce our signature, we can dismount all the antennas from topside and stow them below. But normally when we're at sea, we don't want to operate that way. We want to be seen by other vessels and see other vessels, and we need these sensors and antennas to do that.
Design elements from the Sea Shadow are now being built into a new generation of naval vessels. These warships with reduced radar signatures signify that stealth is coming of age at sea.
Some of the technology that I know is carried over is its faceted hull, and you'll see that now in DDG-51, Arleigh Burke-class destroyers, the LPD-17, very clean superstructures, some gentle angles to the ships. A lot of that has been derived from the testing that was done on Sea Shadow.
Time will tell if stealth's impact on naval warfare will be as dramatic as its effect in the skies. On the sea and in the air, stealth tech may progress beyond what's now imaginable.
The continual research and development of stealth technology is absolutely essential. We've almost developed a level of complacency because we've been so good for so long. We've had the best aircraft in the world, but you have to continue to work to have that. When we go to war, we don't want to go to war with somebody who has a near capability to us or even an equal capability. We want to have overwhelming power. We want to have air dominance, and stealth technology is essential to that.
I think it's important that research and development, places like the Skunk Works, continue to reach out, continue to take risk, and sometimes fail. And I think the real issue today is we have become such a risk-averse society. Failure is just not accepted, that by virtue of not taking those risks, we are not going to discover the next technologies that need to be discovered to truly make our force affordable and invincible.
And don't forget that we didn't see the F-117 until a decade after it first flew. Who knows what amazing stealth technology may already be out there?